So let's take on boundary condition 1, and let's enforce it. So we're going to say now tx, right, our function tx evaluated at x equals 0 is what? It's our general solution up there, that tx at the top, evaluated at x equals 0. So that is c1 times sine of lambda times 0 plus c2 times cosine of lambda times 0. Okay, and that all equals what? That equals 0, right? Because our temperature is 0. So what is this saying? Well, this C1 times 0 goes away because that sine term is 0. Cosine of lambda times 0 is 1. So this is actually saying C2 is equal to 0 for this problem. Right? That makes sense? So that's our first boundary condition. Second boundary condition is going to be the differential one. So let's see. Let me just, actually, at this point, I'm going to rewrite something here. So we're going to say Tx is equal to C1 sine of lambda times x. Okay? That's where we are. So now we have our step 2, which is dt dx. So let's see, dt x dx at x equals w is C1 lambda cosine lambda times w is equal to 0. Okay, lambda can be canceled out of the left-hand side, and so can C1. So we're actually left with this kind of curious thing, which is saying cosine of lambda times w is equal to 0. All right, that was confusing, so stop and make sure you understand it. I have an expression in terms of C1 lambda cosine. This expression is satisfied regardless of the value of C1 and lambda. Right? Those are constants, basically. But it's true, this is always true, when the product of lambda times w, the cosine of that, is equal to 0. Right? The other alternative is to say, okay, C1 is 0. Well, that's, again, not interesting because our expression here would just be that Tx is 0. That's not, like, that doesn't help us. So C1 can't be 0. Lambda, we don't want that to be 0 because then this would be 1. So we're left with this requirement that this term has to be 0. And when is that term 0? It's 0 infinitely many times. Every time lambda times w hits a certain root, right, you get that condition to be true. So this is where this eigenvalue, eigenproblem thing comes from. So let's give some names to this stuff. Let's see, this up here. This up here is called our eigenfunction. This down here, this cosine thing, is called the eigencondition. And then when we actually go through and solve this, we'll find, okay, when lambda times w is equal to what? When it's equal to pi over 2. And when it's equal to 3 pi over 2 and 5 pi over 2, etc., that's when this is satisfied. So these down here are called our eigenvalues. Okay, the eigenfunction is what generates the eigencondition, right, when we enforce the boundary condition. So this eigenfunction stems from the boundary condition enforced at what? X equals 0. And then we get the eigencondition, which comes from enforcement of the other boundary condition. And the eigencondition is what gives us the eigenvalues. And the eigenvalues are the solutions for lambda w at which the eigencondition is satisfied. Okay. By the end of this, you all speak German, I think. So that's the nomenclature. The bottom line is we're just going through this process to find these eigenvalues, which we'll then go back and plug in to help us get some constants. Okay, questions on this part of it? Okay, so what comes next? Then we need to, let's see if we can do this. So we have our step 4. One thing I want to clean up a little bit here. Okay, so this, I guess I didn't have room to write it at the bottom, but what we end up with is this important observation. So we've gone from this X condition problem, right, our PDE or our ODE in X, our X boundary conditions, to T of X, which is T of X equals a constant times sine of lambda X. We just decided that lambda is a bunch of different things. So we can express lambda in terms of some index I. So when I is equal to 1, we'd say 2 minus 1 is 1, so that's 1 pi over 2, or pi over 2. When I is 2, it becomes 3 pi over 2, and so on. Right? We have this repeating condition in terms of our index I. And that's for I equals 1 to infinity. You might come up with an eigencondition or an eigenvalues where I is 0 to infinity or minus 1 to infinity. It's like however you express it. But for this particular problem, it's 1 to infinity. It's valid. The important thing I wanted to say is that, okay, this gives us now Tx, but it gives us infinitely many Tx's because we have infinitely many lambdas. So we have infinitely many constants. So we have now Tx at I for some index is C1 at I times the sine of lambda times lambda Ix. Right? So we have this family of solutions Tx. All right, that's the end result of the previous slide. Now step 4 is we're going to solve the non-homogeneous problem for every eigenvalue of lambda that we have now. Okay, so the non-homogeneous problem, again, was the following. It is d squared ty dy squared minus lambda squared ty equals 0. The boundary conditions, if you remember, were what? The partial temperature with respect to y at y equals 0 is 0. And then t at y equals h is equal to th. So we can go through the same thing we did before where we say, OK, how does this apply to our substitution? And if we do that, we end up with just d squared, or sorry, d squared ty dy squared minus lambda squared ty equals 0. But for every individual I, right? So this is ty, let's see how I did this, tyi, right? And then lambda I here, where lambdas are values given up here. OK, so we have this. We can go back and look at the table, or again, plug it into Maple. For any individual index I, we're going to get the solution. And the solution for this problem is Cauchy and sinh. So this is going to give us ty I is equal to c, some constant. Let's come back to that. So some constant times Cauchy of lambda I y plus another constant times sinh of lambda I y. So I'm coming back to these because let's do some bookkeeping. First, we've already used constants C1 and C2. So let's say C3 and C4. So C3 and C4. And the other thing is these constants have to be true for every index I. Right? They're unique constants for a given lambda. So it's going to be C3 I, C4 I. Right? So now we have a solution for x for every y, or for every I, and we have a solution in y for every I. And we're making some progress, but we need to keep going. So let's see, that was step 4. We solved the non-homogeneous. Okay, step 5, determine the temperature solution for each eigenvalue. Okay, so now the idea is, like I said, we have Tx, we have Ty, for index I. Now we need to bring them back together. And keep in mind, like, what have we done for boundary conditions so far? We've only enforced the homogeneous direction. The homogeneous direction has gotten us to the temperature, or has gotten us to the homogeneous solution for temperature, but it hasn't yet gotten us the actual solution to the problem in the non-homogeneous direction. So we need to take this and combine it back together. So it's kind of as simple as it sounds. What we're going to do is we're going to multiply these two things. So we'll say T, which is a function of x and y, the full temperature now, is Tx times Ty, which is Tx is C1I sine lambda I x times Ty, which is the quantity C3I cosh of lambda I y plus C4I sinh lambda I y. Right? So this here is Tx, this here is Ty. And again, you can see, like, we have our function only of x and we have our function only of y. They're multiplied together. What can we do? We have 3 unknown constants now, C1, C3, and C4. Well, an unknown constant times another unknown constant is an unknown constant. So we can actually consolidate this and just lump in C1 with the other unknown constants. So if we, let's see, where am I here? So yeah, we could do that. I don't think I need to fully rewrite that, but let's keep moving for the sake of time. So, okay, I've combined things. What we could do, let me just show you this. So let's look at the, let's see. So let's look at maple. What I want to do here is get to the same solution really quickly in maple. And what maple can't necessarily do is find the eigenvalues for you. So you have to go through, define what the eigenvalues are. But at this point, we've gotten far enough that I just want to make sure that my temperature solution makes sense and that the boundary conditions that I've tried to enforce in the homogeneous direction are satisfied. So, okay, restart. I'm going to use this command, assume I integer. I guess incidentally, you can say the thing and then comma as opposed to colons. But okay, so we're going to assume I is an integer. We're going to define our lambda. Anytime you say assume, what shows up after it, I'll make this bigger after is a little tilde. That tilde is just noting that there's a modification or an assumption that goes with that variable. So okay, here we're putting in our temperature. Need to figure out the default font for this. So here we're putting in our temperature expression. Right? This is what we just came up with. C1 has been lumped in with C3 and C4. So what I want to do is just check that the boundary conditions are working. So regardless of what my C3 and C4 are, this should be satisfied for any case where we know x. So here this is the condition t at x equals 0, evaluated at any y. So let's look at that. Okay, so uninteresting, and you can't even see it, but it's returned 0. So I've defined this function, t is a function of x and y. I'm evaluating this function at x equals 0. Regardless of what the value of y is, I get back 0. That's our boundary condition, right? So that checks out. The second boundary condition in x was this dt dx at x equals w is 0. So I do the same thing. I evaluate my function, differential, it's 0. So that's good, right? We have proven that we didn't make a big mistake, at least beyond solving for the eigenvalues. And we have a solution that's consistent. The other thing we can do is make sure that the PDE is valid for this. And that would be taking our general expression, second derivative with respect to x plus second derivative with respect to y. And that should give us a solution. OK? So that's a bit of a mess. Let's make this bigger. And maybe not what we would expect, right? Our PDE says that should be true if it's equal to 0. So we have this mess here. Well, fortunately, if we simplify this, it's 0. Right. So, okay, good. So I mean, that's just proving that we didn't make a mistake. I think what we'll do next time is there's like, what, 2 more steps, step 6 and step 7. We're almost there. This is a long, drawn-out topic, but yeah, so that's it for today.